Example E1.3 on page 13 of your text is a problem in which the net electrical force on charge Q1 due to charges Q2 and Q3 is calculated. Now, I'm not going to go through this whole example in detail. Rather, what I want to do is look at one of the parts of this problem, namely the force that charge Q3 exerts on charge Q1, which is expressed in this interesting notation here. And I want to make a few remarks about the notation, about magnitudes of vectors, and about vectors. Okay, so first off, this little symbol here, F sub E, comma, 1, 3. What does that mean? Well, let's look at the diagram. This force arrow is attached to charge Q1, so that is a force being exerted on charge Q1 by something. Well, what that something is charge Q3. With Q3 and Q1 both being positive, they would exert a mutual repulsion. So this force here is the force that charge Q3, exerts on Q1. Now, so what does this mean then, this order? This means electrical force on charge 1 due to or by charge 3. I've written that a little bit bigger here. Now with this notation, it can be a bit confusing. Like if you see these numbers, is the first one the one that feels the force, or is it the one that exerts the force? Well, if you have it written this way, you have to remember, but you could be a little bit more explicit. Instead of writing it this way, you could write it like this. The electrical force on charge 1 by charge 3. Great, that makes it very clear. But again, there's a lot of crap you've got to write in there, so it's kind of cumbersome. You could also write it like this. The force that charge 3 exerts on charge 1. And so 3 on 1, that's a pretty quick and dirty way, knowing that it's on 1, this other thing must be the thing that's exerting the force. And then I left off the E subscript because we're just dealing with electricity right now, so we, probably through context can know what we're dealing with. So, sometimes the moral of the story here is that you can simplify your notation. Okay, so with that being said, I want to say a couple things now about the way we represent the vectors. So we've represented I've represented the vectors here. Now, as part of the calculation, we need to know the magnitude of this vector. Well, the magnitude of that vector is given by Coulomb's law. I can write the magnitude of the vector of the force charge 3 exerted on charge 1. I can write the magnitude of that like this, or even like this. This is another notation our author uses. But what is it? Well, it's given by Coulomb's law. So we've got 1 over 4 pi epsilon naught, or alternately, you can use the electrical constant K. We've got the absolute value of the product of the charges involved, charge 3 and charge 1 in this case. We've got the square of the separation between them. All of this is the magnitude of the electrical force that charge 3 exerts on charge 1. The distance, the separation r between them, that's d in this case. So we got 1 over 4 pi epsilon naught d squared. And in this problem, we're making the assumption, it's given in the problem text that I omitted here, that all three of these charges have the same absolute value, which we're just calling q. So q1 will have the value q, q3 will have the value q, and so that product will just be q squared. And note that the square of anything will be positive, so you can omit the absolute value sign. So that's where that comes from. Okay, so that's the magnitude. How would we express that quantitatively with a magnitude and a direction? So as a vector. So we want to know the vector for which this is the magnitude given this configuration. Okay, so Moore likes to write it this way, but I want to break it up into little bitty pieces, the x, y, and z components separately. So draw your attention down here. First, let's note that this force is totally in the defined x, y plane. It's got no z component. Z would be out of the page or out of the screen, so the z component is 0. Great. Now let's look at the x component. The x component would be along this way, so I need to take the magnitude of the vector, multiply it by the cosine of the angle between that vector and the x-axis. And then I need to note that the resulting component is going to be pointing opposite the direction of our chosen positive x-axis, so I need a minus sign. So I've got this thing times cosine theta times a minus sign, and that's what we have right here. Likewise for the y component, to get the y component would be this way. I need to take the magnitude of the vector times the sine of this angle that vector makes with the x-axis. So I've got that right here. There's the magnitude, there's the sine of the angle, and the projection of this onto the y-axis is already pointing in the positive y direction, so I don't need to throw in a minus sign. And so this is the y component of that force, or that force. Now we can put it all together. There's lots of different ways to do it. I mean, this conveys all the necessary information, but we could use the notation that our I hat and j hat unit vector notation. So I could say that the overall vector is this amount times I hat plus this amount times j hat plus this amount times k hat, the k hat part be 0, and I get this. So that's our I and j notation for the vector. The notation that Thomas More uses is very similar to that, but instead of using I, j, and k, he just likes to use elements of a column vector. So this times that would be the x component, this times that would be the y component, this times that would be the z component. We could, if we wanted, multiply this through and put it in here, multiply that through and put it in there, and so forth, just like we could multiply this through here and there. It's all the same. It's just that we had a common factor, so he pulled that out, keeping this part as simple as possible. So the points I want to make to close here is that this conveys the same information as this, which in turn conveys the same information as this. So you should be familiar with all these different ways of representing a vector. And you should also keep in mind, just to go back to my first point, that there's different ways to write the magnitude of a vector. There are different types of notation. Sometimes from context you can figure out what it means. Sometimes you might want to be more explicit. And then, of course, keep in mind that this is only one part of the problem. If your goal is to find the net electrical force on this charge due to charge 2 and charge 3, well, we've only done part of it. We've taken this one, and then we've got the information breaking this into x and y components. We need to do the same thing for the force on charge 1 due to charge 2, which would point this way. Since this is negative and this is positive, there's a mutual attraction, so Q1 would be pulled toward Q2. And we need to take this and break it up into x and y components, and then add the x components, add the y components, and so forth. Or we could do it all either in our ij notation, working with i's and j's together, or do it in this kind of notation, as is done in the text. So I urge you to work carefully through this example in the textbook. Hopefully this will help you get through it and understand some of the notational pitfalls. Thank you.